Evening viewer, welcome to our Globe TV. Here's the breaking news. Evolutionary biologists at Johns Hopkins Medicine report they have combined PET scans of modern pigeons along with studies of dinosaur fossils to help answer an enduring questions in biology. How did the brains of birds evolve to enable them to fly? The answer, they say, appears to be an adaptive increase in the size of the cerebellum in some fossil vertebrates. The cerebellum is a brain region responsible for movement and motor control. Research findings were recently published in the journal Proceedings of the Royal Society. Scientists have long thought that the cerebellum should be important in bird flight, but they lacked direct evidence. To pinpoint its value, the new research combined modern PET scan imaging data of ordinary pigeons with the fossil records, examining brain regions of birds during flight and brain cases of ancient dinosaurs. Powered flight among vertebrates is a rare event in evolutionary history, says Ame Balanov, PhD, Assistant Professor of Functional Anatomy and Evolution at the Johns Hopkins University School of Medicine and first author of the published research. In fact, Balanov says just 3 groups of vertebrates or animals with a backbone evolved to fly: extinct pterosaurs, the terrors of the sky during the Mesozoic period, which ended over 65 million years ago, bats and birds. The 3 species are not closely related to the evolutionary tree, and the key factors or factors that enabled flight in all 3 have remained unclear. Besides the outward physical adaptation for flight, such as long upper limbs, certain kinds of feathers, a streamlined body, and other features, Balanov and her colleagues designed research to find features that created a flight-ready brain. To do so, she worked with biomedical engineers at Stony Brook University in New York to compare the brain activity of modern pigeons before and after flight. The researchers performed positron emission tomography, that is called PET scan, the same technology commonly used on humans, to compare activity in 26 regions of the brain when the bird was at rest and immediately after it flew for 10 minutes from one perch to another. They scanned 8 birds on different days. PET scans use compounds similar to glucose that can be tracked to where it's almost absorbed by brain cells, indicating increased use of energy and thus activity. The tracker degrades and gets excreted from the body within a day or 2. Of the 26 regions, one area, the cerebellum, had statistically significant increases in activity levels between resting and flying in all 8 birds. Overall, the level of activity increase in the cerebellum differed by more than 2 standard statistical deviations compared with other areas of the brain. The researchers also detected increased brain activity in the so-called optic flow pathways, a network of brain cells that connect the retina in the eye to the cerebellum. These pathways process movement across the visual field. Balanov says their findings of activity increase in the cerebellum and optic flow pathways were not necessarily surprising, since the areas have been hypothesized to play a role in flight. What was new in their research was linking the cerebellum findings of flight-enabled brains in modern birds to the fossil record that showed how the brains of bird-like dinosaurs began to develop brain conditions for powered flight. Behind the report, Globe TV, Delhi, Bharat.